Hi, my name is Jason, and I'm here to talk to you today about some of the common challenges and the potential solutions to achieving seamless application deployments and cluster upgrades with our Elastic Kubernetes Service, or EKS. This is a 300-level session that, in the interest of time, assumes some basic knowledge about AWS, containers, and Kubernetes. Our agenda for today is that we'll start with how best to architecture applications to allow for a seamless deployment experience on top of Kubernetes. Then, we'll cover how to upgrade a running EKS cluster in place with a new machine image for your worker nodes, a new major version of Kubernetes, or both. Let me start by telling you a bit about what inspired this talk. I've spoken with several customers who have believed that taking their legacy applications and just putting them into a container and onto Kubernetes means that they get all of the cloud-native benefits, things like safe and seamless zero-downtime deployments and upgrades. This, unfortunately, is a myth. The challenges around managing state, either in memory or on disk, are the same as they ever were. And, while Kubernetes can make it easy to provision stateful workloads, there are significant repercussions to doing that, which we'll discuss in this talk. You may be wondering why we are starting with the application deployments and not working up from the EKS infrastructure side of things. The reason for that is that, like this busy roundabout at the Arc de Triomphe, we need all of the cars to know and obey the road rules collectively for things to go smoothly as a whole. If even one application doesn't behave in a cloud-native way, then it can mean that cluster-level changes may be disruptive for that application. And thus, you may need to wait for an outage window for cluster upgrades to not disrupt that app. And if you have many such apps, then finding a window when you can disrupt them all at the same time becomes even more challenging. So, what are our considerations with application deployments on Kubernetes? Firstly, there are the challenges of API and schema versioning and compatibility. The most common way to deploy new versions of your application to Kubernetes is using a Kubernetes deployment. What you may not realize is that doing a deployment, it means that you're doing a rolling upgrade. This means that both the old version and the new version are behind the same load balancer at the same time, and the requests from the same client could be going back and forth between those two versions during that process. Can your clients and/or your service deal with this behavior? If you can't deal with this situation of a client being able to talk to both the old and the new versions, then that's what we call a tight coupling, or a distributed monolith. This means that, like these train cars, if one service moves to a new API version, the other that depends on it has to move with it at the same time in lockstep. A tight coupling like this also means that any rollbacks require rolling back both services together as well, which can often delay or complicate your rollback when you need it to work the most. Since one of the main motivations for a microservices-based architecture is that these services can be run by different teams who can deploy their changes independently, this is less than ideal. The other challenge with deploying new versions of your services is that when you deploy a change to the schema for the database behind the service, for example, to accommodate a new column or table to store data for a new feature. The way that this was done in the past was to give a runbook to an IT operations person or database administrator with a bit of SQL that needed to be applied to your production database as a prerequisite for your application deployment. We'll look at how you can automate that process with Kubernetes in a moment. Putting this all together, if you want to leverage the Kubernetes default of rolling updates, you need to be able to ensure that both the clients can still use the previous version of the API when calling your service, as well as that your service can have both versions interacting with the same database before and after a schema change. Versioning your API, perhaps with different URI paths, is one common way to handle this on the API side. On the database side, you should version your schema, embed your upgrade logic into your service's code, or as a Kubernetes init container, as we'll see in a second. Also, limit yourself to non-blocking changes that are additive. For example, add a new column rather than change an existing column. And finally, be specific in your select as to which columns you'd like returned, so when a new one appears in your database, it doesn't break your older versions, since they don't unexpectedly get that column with its select star. If, for whatever reason, you can't make those changes to the app to allow for the rolling updates quite yet, there's an alternative, blue-green deployments. This ensures that your old version stops receiving traffic and interacting with your database before the new version comes up. The trade-off with this is that both deployments, as well as rollbacks, will often entail a disruption when you flip that traffic back and forth. To minimize the risk of possible disruption, customers may want to do these deployments during a change window, when you are at a low point in your traffic, or you have agreed with your customers that it's acceptable to have a brief interruption. So, how do you actually do blue-green deployments on Kubernetes? The answer is to create a second independent deployment for the new version with a different label. You can then optionally test that new version before you send it any traffic, as long as it won't introduce database schema conflicts as we discussed before. Then you can go to the Kubernetes service or the ingress that fronts your application and change its selector to point at your new deployment's label, which flips 100% of the traffic. And after that, you can scale down or remove the old version's deployment at your convenience. Coming back to database schema updates, there's two ways to handle those if you want to orchestrate it within Kubernetes. The first is you can put logic to do this upgrade in your application so that when it starts up, it will check if an upgrade is necessary and do that if required before handing the database connection over to your normal application logic. This doesn't require any changes on the Kubernetes side. If, however, you don't have access to the code or you'd prefer to separate this from your code, then Kubernetes init containers can help here. Basically, in your pod spec, you can say, I want an init container to come up first before my app container. You can then embed a SQL client and your scripts to perform the upgrade in that init container, and only once that process is finished will Kubernetes start your app container. Now, let's look at how pods are shut down, as well as how Kubernetes knows that they're up and healthy as they're scaled back up again. When Kubernetes needs a pod to go away because the node is being drained, then it sends a SIG-term signal, which means please shut down gracefully. Does your app watch for and honor that signal? It then waits 30 seconds by default and gets impatient and issues a SIG kill. If your app needs more than 30 seconds to shut down gracefully, then you could put termination grace period seconds in your pod spec and it'll wait longer for you. Kubernetes also has the concept of probes, which are also often referred to as health checks. The readiness probe controls whether the service should be sent traffic. The liveness probe controls whether the pod should be healed through replacement. And the startup probe says to wait on the other two until the app is fully up and working. Maybe it takes a while on its initial startup, and this allows for that to be handled. Have you configured these appropriately for your app so that Kubernetes is handling them appropriately for you? The default behavior of a Kubernetes deployment is to not use more resources than you currently are during the rollout process. In order to ensure it doesn't go beyond 100% capacity, it scales down the old version by 25% before scaling up the new one. This means that your app needs to be able to handle running at 75% of its capacity during your deployments. Is that true for you today? If you can't deal with losing that capacity and would prefer to err on the side of using more than 100% of the capacity during your deployment, then you can tweak the max unavailable and max surge parameters in your deployment spec file to do so. And if you're doing a blue-green deployment, then you're not impacted by this, as you have full control of the capacity of both of your deployments during the process. As we said earlier, Kubernetes is doing pods the favor of asking them to shut down gracefully and then giving them the time to do that with a SIG term. Ideally, you should be catching that signal in your code and using it to ensure that the pod going away will be as non-disruptive as possible. This code is an example of how to do that within a Node Express app, but there will be similar examples for all the languages and runtimes. You should test if your app behaves as expected here, and if not, you may need to catch that signal and add some logic for it to do so, like in this example. Our next set of challenges are around stateful applications. The first challenge is in-memory state of things like session information. By default, Kubernetes will spread requests evenly across your pods. If you need a particular customer to keep going to the same pod once they've logged in, that requires sticky sessions. Does your app need this? The other kind of state we run into is when an application requires a disk in the form of a persistent EBS volume. The challenge with these is that the volume needs to be unmounted from the existing pod and node before it can be remounted on another, leading to a brief disruption if you want to move it to a new node. Another challenge is that EBS volumes are tied to a specific availability zone. so it ties your pod to that as well. If your application requires clients to keep going to the same pod, sticky sessions, how do you do that with Kubernetes? The built-in service has a fairly limited capability in this regard. It only can do it by source IP address, and its only option is timeout seconds. However, if you use an ingress instead, they allow for many more options, including having stickiness based on cookies, as shown here. So the question is, should you use sticky sessions? The advantage is that if your application needs it in order to work properly, perhaps because without it, a user has to log back in every time they hit a different pod, then it can allow you to deploy that app on your cluster. The disadvantage is that if this pod is unhealthy and restarted, if you deploy a new version of your app, if you upgrade your cluster, etc., it will have a user-facing disruption. Using the previous example, it might require all of the users that have been sticking to that pod to log back in again. So, if you're using this to accommodate legacy application issues, you still have a motivation to improve your application, to externalize this state, and get to a place where these sticky sessions are no longer required in order to improve the availability and operational story for this app, and for your cluster generally. If you need to persist your data to disk with a persistent volume, there's actually 3 options mapping to 3 of our different storage services: EBS, EFS, and FSX for Lustre. Which of them you choose depends a bit on whether you need dynamic provisioning, i.e., for the volume to be created on request within Kubernetes. You can tie that pod to a particular availability zone, and whether you require the volume to be mounted multiple times concurrently. And also, of course, what kind of performance characteristics that you need that volume to have. We have CSI drivers for each option, and while people often choose EBS as their default choice, it's worth looking to see if EFS or FSX for Lustre might be meeting your needs better. If you choose EBS, though, it is both single availability zone and single mount, meaning that any interruption to your pod will also mean an interruption to your app. There are some apps, such as MongoDB and Cassandra, though, that are able to withstand that without interruption while using EBS persistent volumes. So how do they do that? Those applications get away with it as they have their own replication logic, which sends the changes to other pods in other availability zones, who then in turn write it to their own persistent volumes. They then have the logic to allow for the current leader pod to get interrupted and one of the other pods to take its place as the leader. As with sticky sessions, the question of whether or not you should do this is apt. And the answer is the same. If your app requires it to work properly, then it can make sense. But it means that the availability and upgrades of your app and your cluster are compromised, and you will have a brief outage to the app during these upgrades, unless you want the app to work around that itself with application-level replication and leader election. The final application consideration to think about is dependencies. Sometimes you have real dependencies, and things need to happen in a certain order. If we look at this photo of the construction of the Sydney Harbor Bridge, you can't hang the roadway from the arch until the arch is finished. In Kubernetes, we can have ordering required by containers within our pod, such as with the init container we discussed for database schema, or we can have a particular ordering required between the pods of our app, facilitating things like a leader election. The main way Kubernetes provides to solve pod-level dependency challenges is with stateful sets. Stateful sets by default are created one at a time in order, deleted one at a time in the opposite order, last to first, updated in a rolling update in the opposite order, last to first, given stable names that follow them in the format of name-incrementing number, e.g. app0, app1, keeps the persistent volume claims when the pods are rescheduled on another node. And that's it for application considerations. That wasn't an exhaustive list, and I'm sure that there are others, but those are the common ones that I find come up with my customers. Now let's talk about cluster-level considerations. Firstly, the way that nodes are managed in EKS is via EC2 autoscaling groups, which means that they are immutable servers that are scaled and replaced by spinning up new ones from the same Amazon Machine Image, or AMI. So, in order to upgrade them, you don't do that in place, but instead replace the whole server with a new one from the new AMI. We've introduced a feature to help with this process called Managed Node Groups. It has an automated and opinionated upgrade process that will alert you when a new machine image is available. This would be for one of 2 reasons. Either we've released a new AMI, or you've upgraded your Kubernetes version, and it will now offer you the latest AMI for your new version of Kubernetes so that your nodes match your control plane. You can then trigger a rolling upgrade to that AMI that will, as a first step, increase your auto-scaling group by the number of availability zones you're in. For example, by 3 if you're spread across 3 availability zones. The auto-scaling group will balance this capacity so that you have a new node in each AZ. It will then put a taint on the Kubernetes side of all the old nodes. This is to ensure that any pods that are rescheduled during the upgrade process only get moved once to a new node, rather than getting bounced around between a string of old nodes progressively getting decommissioned. The managed node group will then select one of the old AMI nodes and issue a kubectl drain command against it to let it know to remove all the pods from that node. This triggers the replica set or stateful set to notice that it has one fewer pod running, and it should reschedule that pod on one of the new version nodes. Once the node is empty, it will tell the auto-scaling group to terminate that node. This will then trigger the auto-scaling group to notice that it is one fewer instance running and that it should launch a new AMI node. Eventually, all of the old AMI nodes will be gone. The managed node group will recognize the upgrade process was successful and then scale the auto-scaling group back down to its original capacity. The important thing to note here is that if you're using self-managed nodes rather than managed node groups, the last 4 steps are things that you have to do yourself. It's also important to note that if this were the Fargate mode instead, you don't have to worry about nodes at all. Another nuance I find people to have a misconception about, especially if they've come from the land of vMotion of virtual machines between hosts, along with all the in-memory state, is that pods, even in stateful sets, don't ever actually move between nodes. What happens instead is that they're cloned onto the new node from the original pod spec and container image. If there's a stateful set, it also will get the same persistent volume, claim, and name given to the node. It's sort of like instead of shipping a sheep to a different location, you instead terminate it and send the DNA of the sheep instead. The recipient then clones it, and in the case of a stateful set, gives it the same name on the other side. There's also a way that you can declare to Kubernetes the characteristics of your app and how much disruption it can tolerate during changes or upgrades, called pod disruption budgets. You can say for a given app, either a min available or a max unavailable, and then a kubectl drain, amongst other things, would fail if it would violate this disruption budget. Note that each of these YAML specs specifies an API version. Next, we'll talk about the considerations around these in your cluster upgrades. Kubernetes periodically deprecates APIs, and then a few versions later will remove those deprecated APIs. So if you're upgrading to a new version that has just removed a deprecated API that you're still using, you need to make some changes to your YAML spec files or Helm charts first. There are 2 main ways to test if this is the case. First, you could have a production-like cluster, perhaps your development environment, which you upgrade first, and then test that everything still deploys before proceeding with production. Alternatively, there are tools such as deprecation or kubenoTrouble that can either scan your spec files or Helm charts in place, or can scan the deployed items on your cluster and tell you if you have to update your API versions before proceeding with the Kubernetes upgrade. Lastly, there are some add-ons that are part of EKS, namely our CNI, Core DNS, and kubeproxy, and they often need to be upgraded after you've upgraded your cluster. This chart from our documentation indicates whether that's the case and what version you should upgrade these to after your control plane upgrade. The good news is that we've announced a new feature to help here too called Manage Cluster Add-ons. This means that we will manage these add-ons, including upgrading them for you. The other really exciting thing is that we plan on extending this to other add-ons that you need to run on your cluster, such as the plugins to ship your logs, the pod and cluster autoscalers, your ingress controllers, etc. Stay tuned for more managed add-ons to come. Well, we've come to the end of the session. The key takeaways here is that the choices that you make around your architecture and where you store your state can make app deployments and cluster upgrades more complicated and disruptive. In short, Kubernetes doesn't magically solve these problems for you, and often you need to make architectural and code changes to make your app more cloud native to do so. If you can't architect for the Kubernetes default of rolling updates, then you can do blue-green instead. But then your deployments and your rollbacks may be disruptive. If you can't architect for statelessness, then you can use sticky sessions or persistent volumes. But then your deployments and cluster upgrades may be disruptive. And there is a new version of Kubernetes every quarter like clockwork. So you need to either architect for upgrades to be seamless, or negotiate the outage windows to allow for them to be done in order to keep up with this fast-moving project and ecosystem. I hope that was helpful, and happy Kubernetesing on AWS. if you'd like to learn more about our containers or our serverless offerings, we have free online courses as well as paid expert classroom training available virtually to help build your skills in these key areas. We also have labs, white papers, and more linked from our containers and serverless ramp-up guides. Visit aws.training/learning library today. Thank you very much for your time, and please don't forget to fill out the survey.